I will again review the comparison between chapter 11 and 12, and that will be it. We'll finish chapter 12 in 10 minutes. In chapter 11, this is a side-by-side comparison. So it's very important. In chapter 11, we said we have a simple linear regression model. I will keep highlighting with the light blue color. We have a simple linear regression model in chapter 11 where we had only one regressor. In statistics, we call it regressor. Sometimes we call it predictor. In machine learning, you call it feature. Sometimes they call it covariate. They are all the same things. In experimental design terminology, some engineering departments, they call it covariate, feature, predictor, regressor. They are all the same things. So in simple linear regression, that was the model. In multiple linear regression, your model is extended to many features. You have x1, x2, all the way up to xk. How many features? You need to remember this notation. How many features? Not infinite. There are finite number of features. K features. You need to remember this notation K. What is K? Number of features. What is N? Size of the sample. Size of the sample. K is the number of features. N is the size of the sample. Okay. Then from this sample of size N, what did we do in simple linear regression? We used the least square estimation and we found the estimates for those coefficients. We did the same for multiple linear regression. We used the sample of size N and we found those coefficients. What did we do after finding the coefficients? We moved towards the interval estimation and hypothesis testing. We did the same in chapter 12. When we moved towards hypothesis testing, in chapter 12, you don't have a single feature, you have K features. So you come across three situations that we might ask you to test. Number one, test the significance of all the features. Number two, test the significance of one feature. Number three, test the significance of some features. One, some, all. Three cases we can ask you. For example, I give you a multiple linear regression model, y equals beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4 plus beta 5 x5 plus epsilon. How many features? What if I ask you to test h naught that beta 3 is 0 against h1 that beta 3 is not 0? How many features am I asking you to test? One. Which test? T-test. What if I ask you to test h naught that beta 1, beta 2, all the way up to beta 5, all of them are 0, versus at least one of them is not 0. How many features am I asking you to test? All of them. 1 to 5, all of them. Which test will you use here? Full F test. We call it full F test because it's for the full model. What if I ask you to test h naught that beta 2 and beta 5 are 0? Versus at least one of these two is not 0. How many features am I asking you to test? Some of them. For this one, what we call test we applied is a partial F test. What is the meaning of partial? Part. So you're testing for the part of the model. So this is what I'm saying is in chapter 12, you will encounter three types of hypotheses. In chapter 11, there was one feature, so there was only the middle case. In chapter 12, you have three cases. Either test the whole regression or test one coefficient or test some coefficients. Clear? For the whole regression, we have a full F test. For one coefficient, we have a t-test. For some coefficient, we have a partial F test. What do we do after completing the testing? What did we do in chapter 11? We use the regression line. For what? Number one, for estimating the mean of y when x is x naught. Number two, for predicting the value of y when x is x naught. We'll do the same. We'll try to estimate the mean of y when x1 is x1 naught, x2 is x2 naught, x3 is x3 naught, x4 is x4 naught, x5 is x5 naught. And also we'll try to do the prediction of a single value of y when x1 is x1 naught, x2 is x2 naught, and so on, right? So let's take an example that x1 here, y here is your score in major 2, X1 is the study hours. X2 is your score in major 1. X3 is your IQ. X4 is your room number. X5 is sleep hours, right? So I'll have the data on students. I have student number 1, 2, all the way up to, let's say, 20 students. And I will have the data on Y, Y1, Y2, all the way up to Y20. I will have the data on X1, X2, X3, X4, X5. I will have this kind of data file. Clear? In each data file, one row indicates what? The data obtained from one observational unit. One row will indicate the data obtained from one observational units. Once you have the fitted line, suppose the fitted line is y hat equals 7 plus 1.2 times x1 plus 9.7 times x5. Then I ask you that I have a new student whose sleep hours are 7 hours, whose room number is 948, whose major 1 score was 55, whose IQ is 121, and whose study hours are 3.5 hours. Predict the major 2 score of this student. What will you do? Plug in the values in the fitted model and get the value. What if I tell you that I have many students who study for 3.5 hours, who sleep for 7 hours? They all live in room number 947, and so on, the same characteristics, and try to estimate the mean major 2 score of all those students who have this characteristic. What will be your answer? Same answer. So whether you are trying to estimate a single mean value of y or a single value, the point estimate will be, what will happen to the interval estimate? Different, narrower for the first one, wider for the second one. And what is the wording that we use for the interval estimate? Confidence interval for the first one, prediction interval for the second one. Clear? Next, what did we do in chapter 11? We defined a measure that tells you how good is the regression. What was the measure? R square. R square was the measure. What does R square measure? It measures the percentage of variation in the model, which is explained by your regression. So if R square is 0.91, what will you say? 91% of the variation in Y is explained by the regression. What about the remaining 9%? Unexplained variation that goes to the error, which is not explained by your regression. Similarly, in multiple regression, you have R square. Again, R square is SSR divided by SST. If R square is 56.7, what does that mean? 56.7% of the variation in Y is explained by the set of these 5 predictors. What about the remaining 44%? It was not explained by the regressors. It goes to the error. It goes to the error. Now, we saw that there is a problem with R square. The problem with this measure R square is if you keep adding more features to your model, keep adding new predictors, new regressors to your model, R square keeps going up. It never comes down. It doesn't have the capacity to come down. It keeps going up. Worst case scenario, it will stay the same. If the feature is completely useless, it will stay the same, but it will not come down. What we want from a measure like R square is that if the new feature added is good, it should go up. If it is bad, it should come down to tell us real picture whether the newly added feature is good or bad. So what we did is we make an adjustment to the formula of R square, and the resulting measure is called R square adjusted. This formula is given to you in the formula sheet for adjusted R square. Now, what's good about this adjusted R square is that in this model with 5 features, if I add another feature, the starting letter of student's name, is that a good feature for predicting the major 2 score? In this case, the R square adjusted for the new regression will come down as compared to the R square adjusted of this regression, telling me in the real picture that the newly added feature is a useless feature. I should not add it. Clear? Finally, yes. Who decides what features are? Usually, again, this is a question out of the scope of this course, but usually what we do is when we start a real study, we have a target variable in front of us, which is y variable, which is, let's say, major 2 score. As a data scientist, you will sit down with the domain expert and you will ask him, what do you think, what variables can affect this variable? Can. They may not. Can. So you will try to collect a pool of predictors, a very big pool of predictors that might or might not affect y. Once you have this big pool, now from this big pool, you will select some of them. Now we have techniques in data science to select some of them, which are significantly affecting y, and dropping the ones which are not significantly affecting y. But to start with, you will sit with the domain expert and you will prepare a big pool of predictors from where you will select. The last topic of the chapter will be the assumptions of regression model. This is not a very significant topic. What you need to remember is there are 4 assumptions of regression model. Don't write an exam line. They will give you 0. Remember what L stands for, the linearity of relationship between x's and y. I for the independence, the data from one student is independent of data from another student, and each row data is independent. Number 3 is normality. The distribution of error is normal. Number 4 is the equal variance. The errors, they have an equal variance. I will show you through graph how to check these assumptions, but very informal checking. This is a very light topic, which is not covered in detail in this course. This is the whole chapter 12. Now I'll go topic by topic with all the details. First slide introduces the multiple linear regression, and it talks about the importance of multiple linear regression, that in most of the studies, one feature is not enough. There are many features which are affecting y, so we should define a multiple linear regression. The second slide talks about an example. We did that in the previous class. From here, we start for the third slide. If you are interested in testing hypotheses about the coefficients, you will encounter 3 cases. Number 1, we might ask you to test the significance of the whole regression. What test will you use? Left extreme, F test. In the second case, we might ask you to test the significance of a single feature. What test will you use? T test. In chapter 11, your single feature was the whole regression. So the 2 of them were same, giving you the same result. In chapter 11, single feature was all features. So T test and F test, they were equivalent. They were giving you the same p-value. But here, they will be different. One feature is not all features. You have other features now. Sometimes we want to see that if adding more predictors, is it improving the regression or not? So we want to test the significance of newly added features. In that case, the partial F test will be helpful for you. For all these tests, we don't see the calculation details. We don't see the formulas, but in all those formulas, you will see sigma square will be unknown like it was for chapter 11. You will estimate that sigma square by what? MSE. This time, the formula for MSE is not SSE over n minus 2. It is n minus k minus 1, adjusting for the number of features. Again, the shortcut formula will be SST minus SSR. For the whole chapter, remember this equation is very critical. Very, very, very critical. This is almost everywhere. This equation is almost everywhere. That is, the total variation in y is equal to the variation in y which is explained by your regression plus the variation in y which is not explained by your regression. This equation, we will see it almost everywhere. Let's continue. For the second test, which is the testing for the single coefficient, we have already done it in chapter 9. We have already talked about the T test in chapter 9. The only thing that we did not discuss, no, this is the full F test. For the full F test, if you are interested in testing the significance of whole regression, remember in exam, in syllabus, you have written something like this. Did anyone read the syllabus throughout the semester? Yes, good. No, but you did. What is written in R here? Sorry, in red here. That from chapter 12, we don't expect from you to do any calculations. All the questions will be based on R outputs. So in what form we will give you the R outputs? We will give you the R outputs in this kind of form, where we'll give you this kind of table. This table is called analysis of variance table. Sometimes you will see the title of this table as ANOVA, analysis of variance, ANOVA, which is a short form of analysis of variance. In this table, what are we telling you? We are telling you about the sources of variation in Y. What are the sources in variation in Y? There is number one, total variation in Y, which is what? Denoted by SST. Then we said that some part of this variation is explained by your regression and some part is not explained, which goes to the error. So these three numbers will be given to you in this table. Again, some of the questions, they might hide one of them and ask you to find it. How will you find it? That equation. What is the equation? It stays with you for the whole chapter. So sometimes they might hide one of these three and ask you to find it. Then the degrees of freedom for each of the component is given. The degree of freedom for SSR is K. The degree of freedom in chapter 11, it was 1 because K was 1. Number of features was 1. Here it's K. The degree of freedom for error, it was n minus 2 in chapter 11. Now it's general, n minus k minus 1. And the total degree of freedom is n minus 1. Then we'll have a column of mean square where we'll divide SSR divided by its degree of freedom and SSE divided by its degree of freedom. And finally, we'll put them into F formation and we'll get the final value of F. From here, we'll have two options like we have in chapter 11, either to go with the rejection region approach or to go with the p-value approach. Now, let me, again, it's not a part of this course, but let me tell you the spirit behind why we form F statistic like this one on a side note. Again, I will start with the same equation. What is the equation? And from this equation, I have defined F to be SSR over K divided by SSE over n minus K minus 1. This is how F is defined. Okay. Now, in full F test, what are you testing? If the regression is significant or not. That's the thing that you are testing. If the whole regression is significant or not. Clear? Now, what if the regression is significant? It's a good regression. What will happen? What will happen to the top equation? Which component will dominate if the regression is good? SSR will dominate, correct? SSR will dominate. When SSR dominates, what happens to error? It will go down because at the end, the sum is constant. When one of them increases, the other has to go down, correct? When SSE is small, SSR is big, what happens to the F? What happens to the F? It goes to the infinity, correct? So if your regression is significant, F will go to the infinity. Let's talk about the other extreme. If your regression is insignificant, what will happen to SSR? 0. What will happen to SSE? SSE will not infinity, go close to SST because the upper limit for it is SST. The total variation is SST. Total variation is not infinity. Total is fixed. So SSE will go to SST. SSR will go to 0. When SSR goes to 0, what happens to F? Goes to 0. So when your F goes close to 0, your regression is insignificant. When it goes to infinity, your regression is significant. What is the cutoff between 0 and infinity? You have to draw a borderline so that on the left side, you say it is insignificant. On the right side, you say it is significant. What is this borderline called? It's very important line. It's a very critical line. What do we call it? Critical value. We call it critical value. So if you are on the right side of the critical value, you will say regression is good. If you are on the left side of the critical value, you will say regression is bad. And this is what all is explained in this slide. Yes. Assuming that f is continuous, the chances that it will fall on is literally 0. Testing the significance of a single predictor. Now, the good thing here is for the single predictor, again, because we are relying on our output, you don't have to compute the standard error of beta hat. We'll give you the standard error of beta hat in terms of a table, in terms of this kind of table. This kind of table. You see, we are giving you the coefficients. This is what? 71.1955. What is this? B naught. What is 0.9723? B1. What is minus 2.8254? What is 3.28? It's the standard error of B naught. What is this one? It's the standard error of B1. What is 0.61? It's the standard error of, so we'll give you the standard errors. No need to do any calculation. What you need to do is you need to remember that the T statistic is basically the coefficient divided by the standard error. So this 21.68 is basically 71 point something divided by 3. Yeah. If the coefficient is minus, of course, minus. Standard error cannot be minus. It's the square root of the variance. Variance is never minus. Beta minus beta. Yeah, let me clarify that point. Okay. 0. This 0. Usually in regression, we are interested in testing if the coefficient is 0. Usually we're not interested in any value other than 0. So that will be 0 there. Remember the degree of freedom for the t test and for all the f tests, the denominator degree of freedom will be n minus k minus 1. And we have already talked about the rejection region approach in chapter 9, the p-value approach in chapter 9, the confidence interval approach in chapter 9, everything we have already done. There is no difference. It's just that in t statistic, you will plug in something different, not x bar and something different. But once you have the t, the remaining procedure is the same. Exactly the same that we did in chapter 9. So what if I give you a confidence interval for beta 1 and the confidence interval given to you is minus 1.27 and all the way up to 0.76. I tell you this is a 95% confidence interval for beta 1. And I ask you a question, is x1 significant in the regression or not? What will you answer? Is x1 significant? In terms of hypothesis testing, I'm asking you to test H naught that beta 1 is 0 versus H1 that beta 1 is not 0. Beta 1 0 means it is insignificant. Non-zero means it is significant. What will you do? What will be your decision? Scientific decision. How do you make a decision of a hypothesis test based on confidence interval approach? Check whether the tested value belongs to the interval or not. What is the value you are testing here? 0. Does 0 belong to the interval? You will accept H naught. Again, I'm using wrong terminology, but you will accept H naught. And you will say that X1 is insignificant, not significant, non-significant, whatever word you use. It is insignificant. If 0 belongs to the interval, that means you will fail to reject H naught. You will go with H naught, and H naught means the feature is insignificant. You don't want to go with H naught in chapter 11 and chapter 12. You don't want to. You want to reject H naught. For every hypothesis, you want to reject H naught. From the real life point of view, you always want to reject H naught. You don't want 0 to be contained in the interval. If 0 is contained in the interval, that's a bad news. That means the feature is insignificant in the presence of other features. So once you compute the t-value using this formula, you have the option to either use the critical value approach or use the p-value approach or use the confidence interval approach. 3 approaches are open for you. This is important. This is the only new topic of chapter 12. So pay attention to this one. And I will try to develop the intuition behind this test using the same example. Suppose you have a model this model. I'm trying to model the major 2 scores based on study hours, sleep time, major 1 score, 3 features. Okay. From this regression, I obtained an ANOVA table. And from that ANOVA table, I set the total variation in Y. Let's say it was 121. The variation explained by my regression was, let us say, 94. And the variation which was not explained by my regression, 121 minus 94. Let's make it 91 to make the subtraction easy. It is 30, right? 30. Okay. Let's say we gave you this output. This was the result. What is the K? No, not K. Let's say the sample size is 20. Okay. Then what I did is I want to add 2 more features to this model. Suppose I want to add the starting letter of your name and I want to add your room number. Okay. So the model will become beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4 plus beta 5 x5 plus epsilon. I want to add 2 more features to the model. And I want to check that whether the newly added features, are they contributing significantly in the presence of the old ones, or they are not contributing significantly. This is kind of testing the significance of some, not one, not all, some. So if I want you to test the significance of x4 and x5, I want you to test the hypothesis that beta 4 and beta 5 both are equal to I want you to test that they are both equal to 0 against at least one of them is not equal to 0. Now, how will I develop the spirit of this test? Again, I will fit the analysis on this new model, which is having 5 features, and I will obtain the total variation in Y will remain the same, 121. Suppose SSR, it became 92. It was 91. By adding 2 more features, it became 92. A little more variation is explained. Okay. Clear? Now, what I will do is I will take, close the door. I will take all of this and I will put it into the formation of F. What is the formation of F? F partial. It is SSR of the full model, bigger model, minus SSR of the smaller model, reduced model, divided by the number of features that you are testing, which is denoted by R, over SSE of the full model, divided by the full degree of freedom. Okay. What is my SSR of the bigger model? The explained variation in the bigger model, 192. Bigger model with 5 features. What is the explained variation in the smaller model? So by adding 2 more features, how much more variation I was able to explain? Only one. Only one. So an increase in SSR because of how many features? 2 features is only 1. This is the total increase because of 2 features. What is the average increase per feature? Divided by 2. SSR full minus SSR revised is the total increase because of R features. What if you want to check the average increase per feature divided by the number of features that you are testing? R. In this example, 2 additional features that you are adding. Divided by SSE, which was, what is SSE of the full model? 29. Divided by n minus k minus 1. Let's say n is 20. K for the full model is 5 minus 1. This is your statistic. Now, let's again talk about intuitionally when will f go to 0 and when will f go to infinity. What if the newly added features are good ones? What will happen? They will add more to the model. The jump in SSR will be big, correct? The jump in SSR will be big. If the jump in SSR is big, this difference will be big. As a result, f will go to infinity. Same logic as we did for the full f test. What if the newly added variables are not adding something significant, like in this case? I had two useless features. I added them to the model, and the data said that they are not adding significantly. What will happen? F will go close to 0. That means the newly added features are not adding anything significant in the presence of the 3 old features. In the presence of those 3, the newly added are not adding anything significant. In between, again, you have a line to decide. What is this line again called? Critical value, and it is F alpha with V1 and V2, which will come from the F distribution. And we will see how to get the critical value and p value from the F table. Clear? This is the third type of hypothesis. And you will see the same explanation, all of it here. You have a model with the 3 features. You want to add 2 more, and you want to see if these 2 more are contributing in the presence of the old 3 or not. You put them into the formation of F. If F goes close to 0, they are not adding something. If F goes close to infinity, they are. What is the quantification of close to 0, close to infinity? There is a borderline in between them, which is called the critical value. So either you can use the critical value approach, or you can use the p-value approach. What you need to remember are these degrees of freedom. How do you remember the degrees of freedom? You go to the formula sheet. They are not categorically mentioned in the formula sheet. I will tell you how to identify from the formula sheet what are the, where is formula sheet? Here is formula sheet. For chapter 11 or 12, here is the formula sheet. In the formula sheet, where is full F? Here is full F, which is the first test, which is SSR over K divided by SSE over n minus K minus 1. Right? I just wrote the full formula by plugging in MSR and MSE. I wrote the full formula. In every question belonging to F, whatever is the denominator of numerator will be the numerator degree of freedom. We call it V1. And whatever is the denominator of the denominator, it's the denominator degree of freedom. We call it V2. For the full F test, it will be K and n minus K minus 1. But for the partial F test, it will be R and n minus K minus 1. What is R? R is the number of features that you are testing, the newly added features. In the full model, there are 5, but how many of those 5 are you testing? In the slide, you were testing 2. So in your example, R was 2. So what will be the degree of freedom for your question? 2 and 20 minus 5 minus 1, n minus K minus 1, 14. So you go to the F table with 2 degree of freedom for V1 and 14 for V2. If you want to test the full model, you will go with 5 and 14. Full F test. K and n minus K minus 1. Clear? Yes. there is no unique solution. This is what we call a high dimensional data. This is what we call a high dimensional data when the number of features is more than the sample size. If you go back to, again, this question is out of the scope of this course. If you go back to the least square estimation, it will not give you a unique solution. It will not give you a unique solution. Then what is the solution to this problem? There are two solutions. One is to reduce the number of features using principal component analysis. There are techniques in statistics, multivariate statistics, where you can, you took them in 291, right? Where you can merge many features into a single feature. This will reduce the number of features, bring it down to within n, and you will be able to fit the analysis. The other one is there are high dimensional techniques which do not rely on least square estimation. So they will give you the unique solution, even if the sample size is small. It is practical because in this new world of data science, we have a lot of data. Sometimes when we open the data set, it has millions of features and the sample size is hundreds. So one of the things we do is sometimes we do feature selection. Out of those millions, we select what are important for us. If the number of important features are more than sample size still, then we do PCA analysis. We combine many features into their linear combination and come up with some features. But again, outside. Not regression. PCA is not regression. PCA is combining many variables into some variables. Regression is at the end. Once you have the columns ready, then we apply regression. Last thing of this chapter is to make use of regression. Again, what do we use the regression for? Two objectives. Estimation of the mean of y when x1 is x1 naught, x2 is x2 naught, x3 is x3 naught, x4 is x4 naught, and x5 is x5 naught. And what is the second use? Prediction of a single value of y when x1 is x1 naught, x2 is x2 naught, and so on. What about the point estimate for the two of them? Same. The point estimate for the two of them are same, but the interval estimates are different. Again, the good thing is you don't have to do the calculation. We will give you the standard error. You just have to do what? Take the point estimate, take the standard error, plus minus a critical value from the t-table. That's it. You just put it into this formula, and I don't think this formula is given, is it? Is this formula given? It is indirectly given here. Look, indirectly, not directly. It is the point estimate plus minus a critical value times whatever this whole thing is. It's the standard error. It is indirectly given here. The point estimate plus minus critical value times the standard error. It is indirectly given here. The point estimate plus minus a critical value times standard error. It is indirectly given here. The point estimate plus minus critical value times standard error. So the general structure of a confidence interval, always a general structure of a confidence interval is what? Point estimate plus minus critical value times standard error. That's the general structure of the what changes is where does the critical value come from? Sometimes it comes from Z, sometimes it comes from T. So that's the only change. And what changes is what parameter you are interested in. If you are interested in mu, the point estimate will be X bar. If you are interested in P, the point estimate will be P hat. If you are interested in beta naught, the point estimate will be beta naught hat. If you are interested in beta 4, the point estimate will be beta 4 hat. So it depends upon what is the parameter and what is the sampling distribution of point estimate. Second last thing of this chapter is how do you measure if the regression is good or not? The old measure that we defined in chapter 11 was R square. What is the problem with R square? It can only increase or it stays the same. It never decreases. So when you add more regressors, even if those regressors are not contributing significantly, R square will keep going up. So that's why we make some adjustments to the formula of R square. What are the adjustments? We divide SSE and SST by their respective degrees of freedom. Look at this formula and look at this formula. They are similar. Are they? 1 minus SSE over SST. The only difference is, what did we do? We adjusted SSE, we divided it by its degree of freedom, and we adjusted SST, we divided it by its degree of freedom. That's the only difference. So we are adjusting. What is the adjustment based on? The adjustment is based on N and K, correct? The adjustment is based on N and K, sample size and number of features. So how do you interpret this new R square adjusted? You will say, let's say this new R square adjusted comes out to be 56.2. What will you say? You will say 56.2% of the variation in Y is explained by your regression, comma, this is R square, comma, adjusted for sample size and number of features. So you will add another sentence at the end of the interpretation of R square, comma, adjusted for N and K. This is what we are adjusting for, the sample size and the number of features. Last slide says that we have 4 assumptions of linear regression. The first assumption is linearity. That means the true relationship between X and Y is linear. How do we check it? We check it using a residuals plot. I will show you a residuals plot now. The second assumption is about independence, that each pair of observations is independent. The third is normality, and the fourth is equal variance. For the first assumption, linearity, let me show you the 3 plots that are covered in your syllabus, but very from the surface level. The first plot is what we call normal probability plot. The plot name of the plot tells you it is for which assumption? Normality, of course. So what we expect from this plot is we have the points following the straight line. In this graph, what we have on x-axis are the errors, and what we have on y-axis are what would be the errors if they were exactly normally distributed. We have the actual errors, and we have the errors if they were exactly normally distributed. So if you meet the expectation, the plot will be a straight line. But from the data, usually it is not a straight line, but it is close to straight line. If you are close to straight line, you are not far from normality. The assumption is okay. But if you are far from normality, if you see the points plotted something like this, or systematically deviating upwards or downwards from the top or from the bottom, that means normality assumption is violated. The second plot is where you plot the residuals against the fitted values. This plot is for assumption number 2 and 4, for equal variance and for linearity. If there is a straight funnel like this one, everything is okay. If you see a curve, linearity is violated. Curve like this one or this one, linearity is violated. If you see something like this, increasing variance, not equal variance. So the last assumption of equal variance is violated. Like, what is the variance at the start? This much. What is the variance here? Variance is the amount of spread, right? What is the variance here? What is the variance here? So as you go along, the variance is increasing. So that means the variance is not constant. The last assumption is independence assumption, which is tested by just plotting the errors. If you see any pattern, a decreasing pattern or increasing pattern or up, down, up, down, up, down, up, down, any pattern, that means the errors are not independent. If there is no pattern, if this is random, the errors are independent. This is the end of chapter 12. Next class, I will discuss a comprehensive example from chapter 12 covering every single thing about chapter 12.